Okay, so we start more or less where we stopped yesterday. So let's please, Ugo, continue your lecture. Welcome.
Yeah, thank you. In particular, yesterday I forgot to say something. I will start by adding that. So this slide concerns our guiding example, which is the resolution of the singularities of the quotient C3 mod Z4 with the action of Z4 that I specified. So I will call Y the resolution of singularities, and we said that the resulting exceptional divisor is one compact component, which is a copy of the second Hilbert surface, and the non-compact component, which is a C times B1. I forgot to say that actually Y turns out to be the total space of a line bundle, which is exactly the canonical line bundle of the second Hilbert surface. So of the exceptional, of the compact component of the exceptional divisor. This is actually a pattern which shows up also in other examples. And it has it shows clearly that the resolution is crepant because the total space of the canonical bundle of every complex variety is Calabi-Yau. So in particular, it is vanishing first Chern class automatically because it is the canonical bundle of something. So consider the total space, right? In this case, consider as a threefold. And now today I would like actually to speak of three topics, which is probably at least one too much, but I'd like to touch at least very briefly the topic of the fact that these crepant resolutions, being indeed the Calabi-Yau, we may think they carry Ricci flat metrics. So there are examples of Ricci, of Kähler-Einstein manifolds with zero scalar curvature. And I will briefly discuss that, I hope. So one thing I would like to do now, probably the right, place to put it, it's here, is to tell you the fact that all these resolution singularities, crepant resolution singularities, we are considering they are actually moduli spaces, very nice moduli spaces. So the point is that all crepant resolutions of C3 mod G are moduli spaces. And of course, you may ask of what? So I'm going to tell you that. So we consider again what is, well, I will consider two things. First, the ring, the representation ring of G. Okay, so this is, well, the set of all linear representations of the group G, which is a ring under using direct sum and tensor product as the basic operations. And I will need to introduce again the regular representation, which I will call R. Right, so it's the representation of G onto the natural representation of G onto its group algebra. And then we introduce a notion of G constellation. So a G constellation is a G sheaf on C3. So it is a sheaf. Of course, C3 carries the action of G given by its defining representation. And we consider a sheaf on it of vector spaces, which has a compatible action of the group G. So it has an action which is compatible with the action on the base manifold. But we also require one additional thing, such that when we take its global sections, we get the regular representation. Okay, so the standard notation for global sections is this. So I will call F, say, this sheaf, and we are assuming that this is R, okay, as clearly as the representation of G. No? The global section in a natural way are a representation of G. We want it to be exactly the regular representation. And on the set of all constellations, perhaps the set of isomorphic classes, where we say the two constellations are isomorphic when they are as G sheaves. So they have an isomorphism which is compatible with the G action, which I consider a stability condition. And to do that, the stability condition will depend on a parameter, which is a stability parameter. And so we consider the space of such objects. This is actually a vector space that we may think as, for instance, I can consider coefficients in R, the real numbers. So in the space of linear functionals on the representation ring, and we consider a normalization. So the regular representation in particular is an element of the representation ring. And so if we call small theta these objects, we require that theta of R is 0. And then we have a definition which says that a constellation, a G constellation, F is stable or semi-stable if theta of actually the global sections of any subjob or object that I will specify now is positive, where E is a G subsheaf. Who among you knows about stable sheaves will see the similarity with the notions of stability for coherent sheaves, or who knows about quiver representations may more or less recognize something very similar to the notion of stability for a quiver representation. So this is stability. Semi-stability means that we have no strict inequality. Okay. Then we we say that theta is generic if for that value of theta, stability is equivalent to semi-stability. And what happens is that we have a fact. You can show that. I don't know why this writes in a strange way. The fact is the following, that if we consider the subspace of generic stability conditions, this is open dense in theta, and it happens to be the disjoint union of convex polyhedral cones. That we call chambers. Okay, and well, the complement, what happens is that the complement of theta gen, so the complement of the union of the chambers happens to be a union of closed subsets which are irreducible, not irreducible, it's not the correct version. Anyway, they are the union of hyperplanes that are not correct. I mean, we have a wall structure, okay? So the chambers are separated by closed subsets, which are called walls. So I will simply say that they are separated by walls. So, for instance, when theta is two-dimensional, I'm simply saying that we have something like this, right? Okay. So we have this structure. And then we consider, we shall call, well, in principle, you should call M theta the modular space, so the space of isomorphic classes of G constellations of theta stable G constellations. And what happens is that if we have two different generic parameter belonging to the same chamber, then the modular spaces are isomorphic. So nothing happens if you move inside, if you move the parameters, stability parameter inside the open chamber. Something may happen if you touch or cross a wall. So this fact justifies the notation MC. Okay, because at the end of the day, the modular space only depends on the choice of a chamber. Now, what happens is that just by definition, the support of a constellation so the subset of C3 where the G constellation is non-zero is an orbit of G, is a G orbit, just by definition. As a result, we have a morphism from MC to the quotient, simply taking the support of the G constellation. So we get an orbit, which is a point in the quotient. And the fact is that this is two very important facts. The first is that this is a crepant resolution singularities. And the second very important fact is that all resolutions, all crepant resolutions, of singularities are of this kind, are isomorphic to MC for some C, for some stability chamber C. So in this way, you get all of them. Of course, this is a very strong theorem. And I would like to discuss some consequences. And this will go into the direction of fully answering a question of yesterday about the K-theory group of a resolution of singularities. From now on, to be safe, on the safe side, to be sure that everything I will say will hopefully be correct, we assume, now we assume that G is abelian. Now, what happened is that, so there is even a third property, which is very important, namely the fact that actually MC is a fine modular space. This means that it comes with an additional structure, which is a universal G constellation. This means that on the product of C3 times MC, we have a G sheaf, which we call U for universal. So this is the universal G constellation. This means the following, that if we have any family, of G constellations, so this means that they are parametrized by, well, I will write a scheme. But anyway, let's call it, let's think of it as a variety, say a scheme T. So this means that on C3 times T, you have a G sheaf such that for every point in the parameter space, F restricted to C3 times that point, so restricted to the fiber, over that point is a G constellation. Then universality means that there exists morphism from T to the modular space such that, let's say F, such that the family is the pullback of the universal constellation. So in particular is id of C3 times F pullback of U. So U knows all families of G constellation. So this is the usual notion of universal object in a modular space. And when a modular space carries a universal object, it's called a fine modular space. Of course, this is something which comes from some very precise definition about the representability of the moduli functor. But anyway, we are not going into that. Now, what happens? Actually, this is true even when G is not abelian. Now, the universal object sits above C3 mod MC, and we have the two projections, in particular over, say, pi 2 over MC. And then you can take the direct image, sorry, pi 2. Of the universal object. This means the following, that for every open set, say V, you consider the sections over the inverse image. And what happens is that this of course, this happens to be a vector bundle, and it's a vector bundle carrying a representation of the group, and basically it splits according to the reducible representations of of G. So we have a bunch of vector bundles. These are called the tautological vector bundle. Vector bundles. And we have a big theorem which says that, first, these generate the K theory of MC, and the Chern characters generate the cohomology of MC. Right, so so this is the full answer to yesterday's question. Yesterday I was slightly misleading. I was cheating a little bit because in particular I refer to the abelian case, because when G is abelian, of course, all irreducible representations are one-dimensional, and as a result, these vector bundles are line bundles, right? Moreover, these spaces MC are simply connected, and as a result, the line bundles are completely determined by their first Chern class. As a result, the K theory is basically the same thing as the homology. Right, because these generators are completely determined by the associated cohomology class. So yesterday, and then what happens is that we know that the cohomology is generated by Itori, the theorem. We know that the cohomology is generated by the reducible components of the exceptional divisor. So when I said that the exceptional divisor generates the K theory, I was completely correct in the abelian case. In the non-abelian case, it's slightly more complicated, as exactly described by this theorem. All this comes from a paper by Crow and Ishii. Okay. So this is the first thing I wanted to say. I would like to stress the fact that all Krepan resolutions are isomorphic to MC for some C, and particular, for instance, what we did in our guiding case, C3 mod Z4, what we constructed using conic geometry is a modular space of G constellations. Actually, what happens, this is a case which highlights one possible feature, because, as I said, in that case, the resolution singularity is unique. There's only one. And then what happens is the following, that on the other hand, you are going to have many chambers in the module, in the space of stability parameters. As a result, all chambers must give the same resolution. So as varieties, all MCs in this case are isomorphic. Nobody says that the universal object is, and indeed it is not. So we did with some collaborators, Pietro Fre, Anna Fino, Dmitry Markushevich, and more. We studied completely the chamber structure for the resolution in this case. So now it's not easy to understand what these pictures say, I guess. So the fact is the following, that in this case, the order of the group is 4. And then you kill one dimension because of the normalization in the definition of stability parameter. So the space big theta is actually R3 in this case. And what happens that this R3 is split into 8 convex polyhedral cones, which are depicted in this drawing. So for instance, on the left, the dark green thing is a cone, and the central point, you should think it's the farthest point, is the vertex in the origin of R3. So it's a cone which opens towards you, okay? And you have 8 of them. And exactly, it happens exactly this, that we computed all tautological vector bundles, which are line bundles in this case. We compute all of them and we check that moving from chamber to chamber, they change. While the resolution singularity is the same because you just have one. We also studied what happens on the walls. On some walls, nothing happens. They are actually called walls of type 0. On other walls, you can find partial resolutions of singularities. So you find a variety which is still singular, but less than the original quotient. I don't have time to go into the details, but the situation can be studied. I mean, in a very precise way. So now, perhaps I will stop to ask if there are any questions.
I have a question. I'm allowed.
Please.
So, so should they be able to reconstruct a quiver from this kind of pictures that you showed?
The quiver you reconstruct from the action of the group.
But it is somehow encoded in this.
Well, it's something which comes earlier. And then what happens is that when you have the quiver, you consider the modular space of its representations, you get exactly the same spaces.
So
get the MCs
forgot, so theta, the space theta, how do you call it? So what's the name for it? General name?
Theta comes from the group because
No, I'm just a bit lost with terminology. So you use
Yeah,
words like
because
constellations and this.
No, no, this is comes up to the normalization comes before the constellations, because simply you take the representation ring of the group and you take the dual, and this is the space of stability conditions. Then there is a normalization, this one, which says that your stability parameters are 0 on the regular representation. But this depends only on the group.
Okay, thanks.
Well, you see, actually everything depends only on the group. Once you have the group and the action on C3, you build everything here. There's nothing else. It's the only ingredient. Perhaps I will spend 10 minutes on this Ricci flat matrix because, of course, we know Calabi theorem, Calabi-Yau theorem. Sorry, it was a conjecture by Calabi proved by Yau, right? So the Calabi-Yau theorem says that if X is a compact, a complex variety manifold, actually. With the vanishing first Chern class. And omega is a Kähler form. On X, there is a Ricci flat a Kähler metric omega prime on X, such that I mean, which has the same cohomology class. Okay, very powerful theorem. It requires the manifold to be compact. So we are not in that case. And our manifolds are non-compact. And then there is no general theorem. You need to specify some property, some condition on the space. For instance, Tian gave results when your space is the complement of what is called an M-pole divisor in a compact manifold. So we have no such general theorem in the non-compact case. But I can cite two things. Well, there is a case where there is a general theory. And this is the case when X is the canonical bundle of the Kähler-Einstein surface. Kähler-Einstein means that the surface is a Ricci form, which is a constant multiple. It is a Kähler metric whose Ricci form is a constant multiple of the Kähler form. Okay. Actually, what counts for lambda is just the sign. And anyway, in this case, it was done by, it's an old paper by Calabi. Calabi solved this problem in this case. And actually, it's recently generalized. I was working with a student of mine on this. So we have a result. On this generalization to basically to product of Keller-Einstein varieties. But there is a very ample class, which are exactly the resolutions of singularities. And this is, I cannot go into detail. This is due to Joyce. And actually, his result and his classification strongly depends on the asymptotic properties of these metrics. He has a definition of ALE, which generalizes to every dimension the definition given by Kronheimer in dimension 2. And this applies when only the origin is a singular point. I mean, resolution of singularity is exactly in our sense, okay? I'm not going to repeat everything, but exactly in our sense. Cn modulo the action finite group in SLNC. When the singularities are not isolated, so you have some line typically of singularities, you have a slightly different notion. You have so-called quasi-ALE spaces, a definition introduced by Joyce. And this is exactly the case given by the resolution of singularities of C3 over Z4, our guiding example, right? In which case, this is also a canonical bundle of surface, but the surface is not Keller-Einstein. Okay, second, the surface is not Keller-Einstein, it has no Keller-Einstein metric. And indeed, and then, of course, as usual, one thing is to know that the metric exists. One thing is to exhibit it. In the compact case, this is an almost impossible task. And even in the non-compact case, it may be very difficult. So the case solved by Calabi allows to write explicitly the metrics. In this case, we do have and I think it's the first result in this direction. We do have an almost explicit description of the metric. The metric is described in terms of power series whose coefficients are determined by a recursion relation. So we do have some form of explicit form of the metric. So this is anyway just a few words about a general problem, namely the fact that these resolution singularities are crepant, so they are non-compact Calabi-Yau manifolds, and therefore they, in principle, we may expect they carry Ricci flat metrics, and then one can consider the problem of going for such metrics. Okay. This is the second thing I wanted to mention today. And the third is physical application. I will simply do the following. I will show you how does as I was saying, a dictionary between all the geometric and algebraic object structures that I mentioned, and things that you find in some field theories. So I'm not particularly expert from the physical viewpoint. Second, we don't have much time. Now this slide is, of course, is kind of terroristic because it shows an awful Lagrangian, which happens to be a full Lagrangian for so-called n equal to Chern-Simons gauge theory in 3 dimensions, where we have a host of fields. Here they are all described with very funny names like chiralinos and all of that. So we have a field theory with a rather rich field content, right? I'm not going into the detail about that. This comes with what is called the scalar potential for this theory, which contains fields of different kinds. Some of them are components of a moment map. Some of them are called the Fayet-Iliopoulos parameters. Some of them are called Vesey-Zumino multiplets, right? And they are the basic fields over which one represents the supersymmetry of the theory, the starting supersymmetry of the theory. So we have a very rich field content. And then basically, the idea is that the geometry I was talking about refers this following situation. We are dealing with an 11-dimensional supergravity for which we look for brane solutions. And this comes with well, in string theory, it's called compactification. Actually, here there's nothing compact, but so we have what we could call a world volume, which is the 3-dimensional M2 brane, and then we have a transversal space, right? Transversal space, which has 8 dimensions. And in several models, this is actually a real cone over a 7-dimensional space. So it's a real metric cone on a 7-dimensional space. Now, what is then I will just show you the dictionary, which I believe is very interesting. Let me just say that why, at least let me mention why these spaces in particular, this metric cone has something to do with what I was talking about. At the end of the day, at least in our guiding example, but also in many other examples that you have when you consider quotients by finite, abelian finite groups, the situation that we obtain is the following. The exceptional divisor will always have one compact component simply because the origin is always going to produce a singular point in the quotient because we have a linear representation, therefore the origin is a fixed point. And then when you resolve that singularity, you have a component of the exceptional divisor which sits on top of the origin, and therefore it is compact, according to the precise analysis provided by the Itorid theorem, right? The McKay correspondence in 3 dimensions. And the resolution of singularity turns out to be the total space of the canonical bundle of this compact component of the exceptional divisor. So in our standard example, it is the total space of the canonical bundle of the second irreducible surface. Now we can keep, for instance, you can expect that you can put a Ricci flat metric on the space. In particular, this means that you have a metric on the exception, the complex component of exception divisor, which is the base of the canonical bundle. So you have an induced metric on it, and this will give the canonical bundle itself as a line bundle will give a fiber metric to it. Right, so we have the metric on the Hilbert surface, for instance, or whatever it is. So this gives, you take the determinant of it, or of the dual, to be honest, and you get a fiber metric on the canonical bundle. And therefore, you can take the what is called, you can take the cone on this total space of the canonical bundle, and you get exactly a Sasaki-Einstein space, which is this metric cone, which is referred to in this picture. Okay, so our analysis of the resolution of singularities fits completely in this picture, and this allows us to, as I was saying, to establish a dictionary. So this slide is propaganda. So I'm just depicting the situation, describing the situation. There is a one-to-one map between the field content and the interaction structure of a Chern-Simons gauge theory in 3 dimensions with 2 supersymmetric charges. And what I called already the generalized Kronheimer construction, which allows one to solve the quotient singularities of C3, the singularity of C3 mod gamma. The finite group here is called gamma. Of course, I took this slide from another presentation where the finite group was called gamma. And what happens? Well, actually, I already used this sentence a few minutes ago. Everything is fixed by the group, or to be more precise, by the group together with its representation on C3. And therefore, in this dictionary, the entries in both sides are bound to be completely determined by the structure of this finite group together, right, with its specific embedding into SL3C or SU3, okay, which is equivalent. And this is the dictionary, or at least part of the dictionary. You might remember that in doing the scalar quotient construction, the so-called generalized Kronheimer quotient construction, we started from a linear space. Then the linear space had, one takes a subspace of the linear space given by some polynomial condition, and takes a quotient of that subspace respect to some Lie group. And what happens is that the space of linear data we start from physically is exactly the space of the West Zumino fields. And the group with respect to which we take the quotient, which I denote as the projective G invariant unitary group of the regular representation, at the end of the day is what is the gauge group of the Chern-Simons theory. So from the physical side, this is the gauge group. The gauge group intended, as it is often done in physics, as the structural group of the principal bundle, which is involved in the formulation of the gauge theory. As we know, to compute the quotient, you need to specify a moment map. And then you take a level set of the moment map and you make the quotient of it. And the moment map you may remember that in one of the previous pictures, slides, which I briefly showed you, there was a scalar potential where some of the fields were called components of the moment map. So the idea is that the moment map that you have in geometry, you find it also in the physical theory. And the stability parameters were known to physicists many years ago as Fayet-Ilopoulos parameters. The quadratic constraint is actually the polynomial constraint, which in this case is quadratic, which cuts the subspace from the space in the first line of this table on the left. Is actually, this polynomial is what is called the cubic potential in the physical theory. And of course, from the point of view of geometry, all of this culminates into the construction of these crepant resolutions of the quotient, which at some point, when I introduced G constellations, I denoted as MC. And these are actually, from the physical viewpoint, as it happens very often in gauge theory, it's just the manifold of the classical vacua of the theory. So we have a completely complete dictionary, right, between geometry and physics in this case. Now, actually, I'm over. I had quite a few things to say, so probably I ran too much. I'm over ahead of a few minutes ahead of time, but anyway. So I'll stop it here. Thank you.
So thank you, Ugo. Let's thank Ugo also, everyone. Well, we have a lot of time for questions, and I would like to remind you that Ugo will stay with us also for the discussion session. So perhaps there will be some quick questions to the content of this lecture, while a general discussion can be postponed a little bit for the future. So please ask your questions. Yeah, Dima, please go on.
Okay, thank you, Ugo, for your set of very interesting lectures. My first question is quick, is about this connection with physics. So how about the two-dimensional case? So you started your lectures from reviewing the two-dimensional McKay correspondence. Does this have applications to ADS CFT? For example, two-dimensional Calabi-Yaus?
Well, yes, I think that, well, the two-dimensional spaces are just these ALE spaces that we discussed. And yeah, of course, this is the beginning of it. There's a paper by Hitchin, Karlslede, Lindstrom, Rocek, which is a little bit the start of all this, where they discuss in the physical part of it, they discuss nonlinear sigma model, where the target spaces are this ALE space. So yeah, sure, it's the starting point in a way. So what happens in higher dimension is done by analogy with the two-dimensional case.
I see. I'm also a little bit confused. I think you explained it, but maybe you can do it again. It's about, so in the picture that you described, you have an 8-dimensional cone, right? But your spaces that you classified as 6-dimensional. 3.5 dimensional.
Yes, there's yeah, I was cheating in the sense that this is described in a paper that I wrote with Pietro Fre and other people, physicists. For some reason, it's reasonable to assume that, so yeah, one should consider C4 modulo gamma. For now, just because you are completely right, you have 8 dimensions, and you want to consider a situation where you are considering a resolution of singularity, so you should consider C4 mod gamma. And then there are some reason, and I believe the main reason is that, to be honest, one doesn't know much what to do in the 4-dimensional case. So one assumes that this 8-dimensional space is at the level of this singular object is C times C3 mod gamma. So we assume that in one direction, everything is flat and nothing happens, so to say. Yeah, it's a kind of a dimensional reduction, which at least makes sense in some physical models. And it is done because, you know, in that case, we are able to handle the situation.
How about a slightly different case? So I'm familiar with the case of 6-dimensional conifold. I mean, that's a Calabi-Yau, and there's even no metric for it. There's Candela Stella Ossa paper, which is, I think, quite famous. So I don't know if you know how to connect, if this story can be connected.
Yeah, it's a similar situation, but it's not a quotient singularity. But the situation is very similar. So let me, and by the way, it can be dealt with rhetoric geometry, because it's a resolution of the conifold. You have something which is an equation of the kind of the type like this, the singular object, right? Which is inside C4. So, right, it's a cone with a singularity at the origin. It is a toric thing, because what you do is that you take 4 rays with a property that, as you can read from the equation, they should satisfy this condition. And then you consider the cone generated by them. So we have 4 of them. As a result, this is not a basis for Z3 because they are 4. So you have a singular space, which is the conifold. In this case, the resolution of singularity may be done, and you have to do that if you want it to be crepant. It's done in a slightly different way. I'm sorry for the drawing, but I'm unable to give it any 3-dimensional appearance. So you should think that these are 4 rays generating a cone, okay, which has 4 generators in 3 dimensions, okay. Instead of adding, you can split this cone adding a ray, but then the resolution that you get is not crepant. Instead, what you do is you split this cone into 2 by adding a face. So you take the face generated by 2 opposite vectors, right? And from the point of view of toric geometry, in the same way as rays correspond to divisors of codimension 1, faces correspond to codimension 2, so they are curves. So what you are doing now is that you explode the origin to get a curve, not a surface. This is called a small resolution. Actually, you can do it in 2 ways, because of course I could have chosen another face, and the relation between the 2 resolutions that are isomorphic is that you contract a curve and you explode another. It's called a flop. in algebraic geometry. But anyway, what happens is that down the resolution of singularities is the total space of something of this thing. Is the total space of a rank 2 vector bundle on P1. Since the canonical bundle of P1 is -2 and 2 minus 2 is 0, it happens that this is Calabi-Yau as well. And this is what Candelas de la Ossa studied. And applying, they don't mention Calabi, but they apply exactly Calabi's trick to get a metric. The same, they applied the Calabi's trick. They don't mention it because probably they didn't know it. Calabi's paper is much older. But they do exactly the same, and they construct a Ricci flat metric, which is what they describe in their paper. Not completely explicit what they do, it can be done more explicit, but this is what they do.
Okay, thank you.